All right, so for today, you're going to need to look at an electronegativity chart. There's some that were handed out in class, there's some that are available online, if you're working ahead. But you are going to want to have an electron negativity chart kind of available for this part. So today we're going to be looking at polarity, essentially what makes a molecule have a partially positive and a partially negative side. Really, we're looking at two ways a molecule can be polar. The first way that we look at is essentially if we can kind of like cut a molecule in half and have electrons on one half and bonded atoms on the other. So if I'm looking at oxygen here, if I kind of do kind of like a dashed line to indicate that I'm cutting this oxygen in half, I have one half that has these pairs of electrons on it. The other half kind of has these hydrogens here. So essentially where I have electrons, that's going to make this molecule look like it's partially negative on that end. And the other side is going to look kind of partially positive. And we kind of use this, I believe that's the Greek letter sigma. I'm probably wrong on that, but really it's a Greek letter. It just means partial charge. So this oxygen looks like half of it has electrons, the other half doesn't. So I would say that this molecule is in fact polar because we have these two halves to it. That's really it. Like, so if your shape has one part of it, one side that has kind of electrons on it, it's a polar molecule. The other thing we can look at are those electronegativities. We're looking at the differences between electronegativities, to which you might be asking, Mr. E, what's electronegativity? Well, I'm glad you asked that question. Really, electronegativity is how badly does a certain element, want the electrons on another atom? It's a scale that goes from 0 to 4, with 4 being the most. Uh, Fluorine is the only element, the only atoms that have an electronegativity of 4. Like they want other atoms' electrons really, really, really bad. So they just said that's 4. Whereas your metals will have them, lower around the 1, sometimes less than 1, because they generally don't care about, taking electrons, stuff like that. So in this case, kind of done with that guy. We're going to also look at it a little bit here. So electronegativity, and I said we're looking at the differences between these two things. So if I'm looking at this, if I check an electronegativity chart, the electronegativity for oxygen is 3.5. The electronegativity for hydrogen is 2.1. So in this case, this oxygen, we're going to say wants electrons at a strength of 3.5. I'm looking at each bond separately. So let's look at this bond first. This hydrogen wants the electrons with the strength of 2.1. And I said that we're looking at the differences between those. So 3.5 minus 2.1, 5 minus 1 is 4, 3 minus 2 is 1, 1.4. That's pretty big. What we're going to find is, if I could spell, let's go polar bonds occur when the electronegativity difference is greater than 0.4. Okay, so if the difference is 0.4, it's not polar. If the difference is 0.5, that is polar. Okay, I think that's the general rule we're going to use. Polar bonds occur when the electronegativity difference is greater than 0.4. So, okay, that shifted on me. That's cool. All right, so we know that the bonds between the hydrogen and the oxygen, that difference was 1.4. That's definitely a greater than 0.4. That means the oxygens are even pulling the electrons in this bond closer to it, because that oxygen it's essentially stronger. It has higher electronegativity. To indicate that on here, really what we would do is we're going to draw kind of this arrow that kind of has a plus side on this side and an arrowhead towards the oxygen. Really what that says is in this bond here, the electrons in this bond are being pulled to the oxygen. They're spending more of their time around the oxygen. So it's going to leave that hydrogen looking partially positively charged. And we're going to find that this distance difference is the same. So we have the same thing here. That's just some notation you're going to find in textbooks. So really, oxygen is doubly polar. It's polar because it has the electrons on one side. It's also polar because the oxygen pulls the electrons away from the hydrogens. In fact, that is why water tends to be a really, really polar substance and makes a great solvent, but that's foreshadowing things to come later on down the course. All right, I'm ready to move on from H2O. So HCN. First off, what's my central molecule? I'm going to guess carbon. Everything, the hydrogen's connected there, nitrogen's connected there. Next question is, can I cut this carbon in half so I have electrons on one side? Well, this carbon doesn't have any pairs of electrons, so I know my shape alone isn't going to get me to whether or not it's polar. So now I need to look at electronegativity differences. So the carbon, the electronegativity for carbon, if you check an electronegativity chart, is 2.5, okay? Hydrogen, we already found to be 2.1. Nitrogen's one I haven't looked up yet. Nitrogen, I'm checking a chart, and it looks like it has an electronegativity of 3.0. All right, so now I'm going to go through and I'm going to look at the carbon-hydrogen bond and then the nitrogen-carbon bond. When we do this difference stuff, whoever's going to take the higher number minus the smaller number. So in this case, so the carbon-hydrogen bond, we're going to take carbon, so we're working with 2.5 and 2.1. 2.5 minus 2.1, that difference is 0.4. And that is right on the edge, but it's not polar. Okay, so the carbon-hydrogen bond, that's not polar. Essentially, these electrons are spending an equal amount of time around the hydrogen and around the carbon. All right, so now let's check the carbon-nitrogen bond. Nitrogen we said was 3.0, carbon's 2.5. So bigger minus the smaller, so I have 3.0 minus 2.5, and that's going to get me a difference of 0.5. 0.5 is greater than 0.4, so this bond right here is polar. It's going to be polar towards the bigger number, so this bond is polar towards the nitrogen. So in this case, the electrons in these three bonds here are being pulled towards the nitrogen, and it's going to leave kind of this carbon part partially positive. So essentially positive end there, negative end there. So this bond, this molecule, I should say, is polar because essentially we have this uneven pulling. That'll be really important for this next part. Essentially, the electrons being pulled in kind of this asymmetric, this one-sided way towards the nitrogens. All right, so here we have CCl4, carbon tetrachloride. Really, my carbons, once again, carbons will never have a pair of electrons on them, so I know that shape alone cannot make this thing polar. So then we're going to go through and we're going to check electronegativities for each bond there. So carbon, we already looked up, has an electronegativity 2.5. Chlorine, you check your electronegativity charts. I'm showing it has an electronegativity of 3.0. All right, so now this bond alone, so the carbon-chlorine difference, or chlorine-carbon difference, is going to be the bigger one, 3.0 minus 2.5. That looks like something I just did. That difference is 0.5, which is enough to make that bond polar. So that makes this bond polar. That also makes this bond polar. And that bond polar. And then spoiler, that bond's polar as well. So each of these four bonds is polar. But now in this case, I'm having electrons pulled in all directions equally. These things are equally spaced out. Each chlorine's pulling electrons away from the carbon just as much as the other chlorines. In this case, though, I don't have a way that I can cut it where I can say this half's positive, this half's negative, because in fact, the whole outside looks negative, and it can only be polar if one side of this molecule is positive. So in this case, even though all of my bonds are polar, the whole molecule isn't polar. There's no positive and negative half to it, because you need that to be polar. I know that's about as clear as mud. We're going to be working with it in class a bit. I'll be answering questions. We're going to have a couple days to review to help with this as well. But in a nutshell, that's pretty much the two ways you can tell if something's polar is A, if its shape has a side with lone pairs of electrons on it, and B, if we have uneven pulling of electrons due to differences in electronegativity. Good luck with that and have fun with the practice.